before we proceed? Okay, let's continue then. You can still see the slides, right?
Yes.
Okay. All right. So we've finished fault trees, and then we enter the next non-space model type. And here I will show you the example from Boeing. So the next model type is called reliability graph. In Sharp, it is called rel graph. So we have a set of nodes and set of edges, and an edge represents edges represent components that can fail. There is a source node and a target node or sink node, and system fails when there is no path from source to sink along which all components are working or edges are working. So this can be thought of as a non-series parallel reliability block diagram also, and it has other names such as ST connectedness problem, source to terminal connectedness problem, or a network reliability problem. So this is a fairly well-known problem in the literature on reliability theory. And solution methods that are known for rel graphs are first find all min paths, after which you need to do what is called sum of disjoint products. The second method is binary decision diagrams. And the third method is factoring or conditioning. And fourth method is using Monte Carlo. First two of these methods have been implemented in Sharp, namely define min paths followed by SDP and VDD. And now come to Boeing or avionics in general. When a new plane is developed, the manufacturer has to do reliability analysis of each major subsystem of a commercial airplane, and then this analysis has to be shown to Federal Aviation Administration in the United States here for certifying the plane. And so I'm going to show you a real-world example from Boeing Commercial Airplane Company in this regard. So the reliability analysis of Boeing 787, when it was to be carried out, when Boeing 787 was ready to be certified, what happens is that the most of the subsystems are improved versions or modified versions of the subsystems used in earlier planes. Sometimes my animation doesn't work as well as it should. This should be the first one. And so models are also modified version of the earlier models. But occasionally, there is an entirely new subsystem. So Boeing 787, they had to put in an entirely new subsystem called current return network. Now, I'm not an aerospace engineer, but my rough understanding is the following, that earlier planes before Boeing 787 used metal for the body. But in 787, they use composite materials. And therefore, the conductivity is not there. Now, earlier, because the metal frame, when a lightning strikes, it will absorb the lightning. But because of the new frame, which is not metal, to solve the lightning problem, they had to implement a new subsystem called current return network. So since there was no previous example of current return network and therefore no previous model, they had to develop a new model from scratch for the current return network. Now, it so happens that some of my former PhD and postdocs are in Boeing Reliability Engineering Group. So they were given this task. They were very excited. And then they found, after some analysis, understanding of the system, is that this can be modeled as a reliability graph. And so they were very excited. They called me up and they said, we are going to model this as a reliability graph. And since Sharp has this model type, we will be using Sharp. Remember that within Boeing's internal tool, Sharp is the one of the engines. So that makes me very happy if you are able to use it. So current return network was modeled as a reliability graph. which consists of a set of nodes and edges, if you remember. And edges represent components that fail, and source and target nodes. And the system fails when there is no path from source to target. And we are interested in computing the probability of a path from source to target. So very well put problem, very simply stated problem. So so this is, I'm not sure of exactly the same problem, but something similar. There is the source node and the target node, and edges here, each of the edge can fail. Let's say it's a simple probability of failure given for that. And I'm interested in the probability of there is a path from source to target. So the problem is very well known. Solution methods are also very well known. And two of them are implemented in Sharp. So the two implemented ones are min paths followed by SDP or BDD. Boeing tried to use Sharp. My students tried to use Sharp for this problem, but after some time, some effort, they called me up and said it doesn't work. And of course, I need to tell you why and how we solve the problem. So the reason was very simple. In this particular example, real-world example, we found that the number of min paths from source to target was estimated to be 4 trillion. 10 to the 12 is trillion. Now we see such numbers only we talk about budget deficit in the United States, that many dollars or whatever. But 4 trillion is the number of paths from source to target. So there is no way in the world we can generate. So the algorithm is, one of the algorithm is find all the min paths and do the probability of the union of these many min paths. There is no way in the world anybody can solve this problem. But the problem has to be solved, right, in order to certify this subsystem and therefore certify the plane. So they asked me, what can we do? I said, I have an idea, and I have a very good graduate student that I can send you. And idea is actually, most useful ideas are very simple. Suppose that instead of all the min paths, I take a subset of min paths. Then I know that the probability I will get will be less than equal to the final correct probability, right? But also, with respect to such graphs, there is a dual. Just as min paths, there are something called min cuts. So if from all the min cuts, I take a subset of min cuts, then I get probability the other way. These two will form the bounds. So one is the lower bound on reliability, the other is upper bound on reliability. And if these two bounds are closed, I'm done. I don't care however many min paths and however many min cuts the system has. So with this simple idea, I sent the student, Daji Wang, to Boeing. And it turned out that he was able to develop a very good algorithm for doing this and implement that in Sharp and help solve this problem in a very reasonable time. So let me show you so this shows, this is the unreliability upper bound and unreliability lower bound within 900 seconds of computer time. So it turned out that this very complex, intractable problem could be solved by this very simple idea in a very reasonable time. And Boeing liked this new algorithm so much that they decided to patent the algorithm. And so in 2000, this work was done in 2008, I think, and it took a little while to get the patent done. And therefore, we had to hold the publication of the paper. Eventually, we published the paper in EJOR, European Journal of Operational Research, in 2014. And actually, there are a lot of other interesting things about real problems. So after having solved the problem, it turned out that Boeing went to FAA with this particular solution and the model and so on. The Boeing then asked them what tool was used to solve this problem. And Boeing obviously said that Sharp and IREP. Then the next question FAA had was, did the development of these tools, was it based on a standard from DoD or DO 178B? So now Boeing asks me whether you use DO 178B to develop Sharp. And they sent me a 600-page document to verify that we used Sharp. I had never heard of DO178B, and Sharp has been developed over a 30-year period with many, many different students and others and so on. So I thought I have come to the hardest part here. I have solved the problem, but really not solved the problem. So I went through, in my mind, all different things that were done with respect to Sharp, and I put it together in what I call the validation document, and somehow FAA was able to say okay with it. And now they tell me that these algorithms and Sharp are always used for modeling current return network subsystem of any other Boeing commercial aircraft since Boeing 787. So, so far, what we have dealt with are reliability block diagrams, REL graph, and fault trees. And it can be shown, has been shown, that the modeling power of reliability block diagram is the smallest. Better one is REL graph, and best one is F tree among these three. And so series parallel reliability block diagrams and fault trees without repeated events are equivalent. REL graph is more powerful than reliability block diagram since non-series parallel behavior can be accommodated. Fault trees with repeated events are even more powerful than REL graphs. But the most scalable method among all this is the bounding algorithm that we developed for REL graphs for Boeing and implemented in Sharp. And this needs to be and can be extended to fault trees and has not been done. So some of you who want to help me with improving Sharp, you are welcome to approach me. And so we have put together this particular chart of power of representational power of these model types. RBD and fault trees without repeated events are equivalent. Reliability graph is more powerful than either one of them. Fault trees with repeated events is most powerful. And much more power is there in the state space models, which we will discuss next. So to summarize, non-state space methods that we have discussed so far are easy to use, intuitive, and have relatively fast algorithms for solving for system reliability, system availability, system mean time to failure, and to find bottlenecks. But the key assumption that was necessary in order to do this is that components behave in independent fashion for both failures and repairs. Independent failures and independent repairs. And the algorithms I've just repeated here: series parallel composition, the early single slide I gave you, factoring or condition I didn't explain, but has been explained in the books. All min paths followed by sum of distant products. We talked about briefly in the context of REL graph from Boeing. Binary decision diagrams I have not introduced to you, but is there in the books. And the bounding algorithm I briefly mentioned is given in the book and the papers. But, and all the above are implemented in Sharp. But the independence assumption was a key in order to solve these problems. Whereas failure repair dependencies are often present in real systems. And these model types that we've discussed cannot handle these dependencies. And so we have to go to something else in order to capture dependency. And what kinds of dependencies? Shared repair, warm or cold spares, imperfect coverage, non-zero switching time, travel time for repair person, reliability repair, all kinds of dependencies do exist in real systems. So what we have described so far is not powerful enough, not able to capture this dependency. So we need to do something else. So independence assumption is often unrealistic. And there are, I've listed here more types of dependencies in real systems. And this paper that we wrote in 1997 lists some of these dependencies. So the alternative to represent dependencies is to use state space methods. And the simplest example of state space methods are Markov chains, or continuous time homogeneous Markov chains. So to model complex interactions between components, we need to use paradigms like Markov chains, or more generally, state space models. And many examples of dependencies among system components have been observed in practice and captured by homogeneous continuous time Markov chains. And extensions to continuous time Markov chains using reward rates makes them Markov reward models, which makes the computation of measures of interest relatively easy. And more on Markov chains can be found in my old book called Blue Book, in my Q network book called White Book, and of course the green book that we are currently discussing. So analytic methods wise, we have covered non-state space methods, and now we are going to cover state space methods, particularly using continuous time Markov chains. Now, Markov chains, I've given you some simple examples. So this is a model of a Linux operating system that we used for IBM's Blade Center and IBM SIP that we're going to describe later. So suppose that the operating system is up and running, and after some time it fails. Failure rate of the operating system is assumed to be lambda sub OS. When the operating system has failed, it may be that there is some detection delay before you actually realize that it has failed. So there is a detection rate, delta OS. After this small detection delay, you know that operating system has failed. So what you normally try to do is reboot the operating system. So beta OS is the rate at which reboot occurs. But a reboot may or may not be successful. Let's assume that the reboot is successful at the rate with the probability BOS. And with probability 1 minus BOS, reboot is not successful, in which case we will need to call somebody from OIT, Office of Information Technology, and that's the travel time or notification time or whatever, and they will then patch the operating system perhaps. So what we have here in this simple model is detection delay, imperfect coverage, that is, how reboot may be covered with probability BOS and not covered with probability BOS. That is, failure that occurred, reboot might be able to cover with some probability and not cover with some other probability. There is travel time for the person who helps you repair and actual repair time. So this is an example of an availability model which introduces realism rather than simply having mean time to failure, mean time to repair, where there is no realism. So when you introduce real phenomena, real events in the system, then you need to go to state space models or Markov models. Now, availability model will have no absorbing state. The Markov model of an availability of a system has no absorbing state. Whereas we can convert this into a reliability model in which there will be an absorbing state. So in this case, after the operating system reboot is not successful, system is considered down, and of course it will need to be patched and so on. But this is a reliability model because there is an absorbing state. So reliability model will have one or more absorbing states, whereas availability model will have no absorbing states. And if you wanted to, you can solve these models by inputting into SHA either graphically or textually to get the reliability or availability of the system, as I have done here. Now, models can get even more complex. So while developing the model of the WebSphere application server, working with IBM engineers and repeated questioning of what happens after a failure, I came up with a more complex model of the IBM web server, the app server, WebSphere application server, where we found that there were 3 different methods of detecting a failure, one by workload manager, another by node agent, and if both of them don't work, manual detection. We also found that recovery after a failure is detected can be done by node agent by means of auto process restart, or manual recovery can be done by manual restart, node reboot, or node repair. And all this is reflected in this model, in which the delay of each detection and recovery agent as well as probability of success or not success of each of these detection or recovery agents are included. And by the way, there was no document or no one person had this information about what happens after a failure. That is, all the steps in the recovery process were obtained by my repeated questioning, loaded questions. I will ask, okay, after a app server fails, is there a detection of the failure? And 1 week later, the question will come back. Yes, there is a detection by workload manager or a node agent. Then I will ask them, is it possible that workload manager fails to detect? Is it possible that the node agent fails to detect? And they will come back with, say, yes, that is true. And then I said, what then? Then they say, okay, manual detection. Similarly, with respect to recovery, okay, so let's say that node agent is detected a failure. Then what? Well, there is an automated process restart. Is it possible that the automated restart doesn't work? They said, yes. I said, then what? Then there is manual restart. I said, okay, manual restart, is it possible it doesn't work? They say, yes. Then what? They will say node reboot. I said, is it possible node reboot doesn't work? They say, yes. Then what? There is repair. So all this is discovered by my repeated questioning. Of course, if I didn't ask these questions, they won't answer them, then there will be a two-state model that says system is up and then it's repaired. And all the model will be wrong, none of the realism is included, and you get junk output because you have not really understood the system. You have not asked the right questions. So in this case, this is what is called the escalated levels of recovery. If one recovery method doesn't work, then you use another one. If that doesn't work, then you use another one. If that doesn't work, you use another one. And the simplest one is tried first, and so on. So delay and imperfect coverage in each step of detection recovery is modeled here. And so such kind of details is what Markov models require you to. Markov, of course, including such kind of details, you need stage space model, and the simplest version is the Markov model. So when we have a Markov model, in this case, homogeneous continuous time Markov chain, it is represented internally by a generator matrix, which we label as Q. And we have efficient scalable algorithms that are known and implemented in software packages such as Sharp and SPNP and many others. So steady-state behavior-wise, if you want steady-state analysis of the Markov model, we are solving a vector matrix equation phi q equal to 0, subject to phi I equals 1. So this is a linear system solution is what we're doing, except that the Q matrix may have million by million state. It's a million by million matrix, not just 5 by 5 or 2 by 3. And transient behavior, we are solving Kolmogorov differential equations, which are ordinary differential equations, initial value problem, d pi by dt equals pi t q. Once again, Q may be million by million or 10 million by 10 million. And we can also do what is called cumulative transient behavior, in which we are asking for the integrals of the state probabilities. And we can also ask for derivatives of the probabilities with respect to these the parameters. Parametric sensitivity functions can also be computed. And whenever we talk about Markov model, somebody will ask a question, but what about the assumption of exponential distributions you made? If you assume homogeneous continuous time Markov chains. Well, all these assumptions can be relaxed by going to semi-Markov process or Markov regenerative process or phase type expansion or using non-homogeneous Markov chains. In the new book, green book with Andrea Bobbio, there is a separate chapter on semi-Markov and Markov regenerative process. There's a separate chapter on phase type expansion. There's a separate chapter on non-homogeneous Markov chains. And of course, there are several chapters on Markov, continuous time Markov chains and Markov reward models. So the question then is, for a given problem, should I use my fault trees that I've given you earlier, fault trees, reliability graphs, or Markov chains? Well, Markov chains have the capability to model all kinds of dependence, all kinds of fault tolerance, recovery, repair, as I've tried to show you by simple examples. all kinds of dependencies can be modeled. We can also model contention for resources and concurrency. That is, we can do performance modeling, not just dependability modeling. And we can generalize the Markov reward models for degradable systems and therefore what is called performability modeling, combined performance and reliability and availability. We can relax the exponential assumption by going to SMP, MRGP, NHCTMC, or phase type expansions. We can model performance, availability, performability, survivability, resilience, and all of the above. So maybe we found a panacea in Markov and state space models. But there is a big difficulty, and the big difficulty is that the number of states will be very, very, very large for any reasonable system, so as to be impossible to deal with the overall Markov model of the system. So what do? Markov models modeling interdependence among components are needed. Simple model types such as RBD, fault trees, etc. do not suffice. And we need to use Markov and other state space model types. But state space explosion is a very big problem. So what do? So problems with state space models and their solutions. State space explosion or the model largeness problem or scalability problem of state space or Markov models. One solution that has been advocated is the use of a high-level formalism such as stochastic Petri nets and stochastic process algebras for ease of specification and automated generation, storage, and solution of the underlying state space, underlying Markov model. So we can come up with notations that are so powerful, higher level, that the description of a complex system can be done very efficiently or succinctly, and an underlying package will generate the model automatically, store and solve, so that a large Markov model you don't have to, the user doesn't have to come up with and solve. And this method of approach to largeness I have called largeness tolerance, because large model will be generated, will be solved, stored, and will be solved. Therefore, we are tolerating largeness. We are simply hiding the largeness from the end user, modeler. So let's see some examples. One example, there are many, many, many examples, not only in my books, but many papers. But this particular example I've chosen from one of my papers in 2014, when IBM Research Cloud, they invited us to help them model. And in this research cloud, there were 3 pools of physical machines. Physical machines are divided into 3 pools. To reduce power usage costs, physical machines are divided into 3 pools. One pool is called hot pool. All the machines in the hot pool are already configured. Their virtual machines are already configured. So there is no delay in allocating that. So performance is high, but the power usage is also high. On the other hand, when a machine is in a cold pool, then it takes a while when a virtual machine has to be allocated, but the power usage is low, and a warm pool is in between. So this made a problem very interesting, and similar idea has been advocated by Intel. So we had done performance model, we had done availability model, we have done a power model, and also optimization model. What I'm describing here is only the availability model. So physical machines can fail and can get repaired, and the system will be up as long as a minimum number of operational hot physical machines are up and running for the system. And so if the number of physical machines in the hot pool goes below the minimal threshold, then the PM physical machines from the warm or a cold pool might migrate to the hot pool, and upon repair, they migrate back to the original pool. So this migration introduces a very interesting kind of dependence among the three pools. So assuming everything exponential, let's say, we will have a Markov model, but this Markov model will be too large to construct by hand because they are interested in hundreds of machines in each pool or thousands of machines in each pool. And so therefore we use a high-level formalism of stochastic petriness. And the flavor of stochastic petriness that we have developed at Duke in my group is called stochastic reward net. Stochastic reward net models can be automatically converted into underlying Markov reward model and solve for the measures of interest such as downtime, steady state, instantaneous, interval availability, reliability, derivatives measures, all numerically by forming and solving the underlying matrix equations that I briefly showed you available. So this is analytic numeric solution as opposed to discrete event simulation. And the details of the methods are given in this chapter of a book in 1993. So this is a high-level model using stochastic reward net of the IBM Research Cloud for the availability, that is failure repair model. And I'm not going to go through this, just a lot more is available on this paper and elsewhere. Stochastic petrinets and reward nets will be another tutorial by itself, which I have offered a long time ago at Symmetrics. So this particular place holds the initial number of hot machines, machines in the hot pool. This place indicates the initial number of machines in the warm pool. And this place indicates the initial number of machines in the cold pool. And the machines can get failed and get repaired, and there is a migration from one pool to another, and there is a migration back. So the SRN model, stochastic reward net model, is very succinctly able to express the model for any number of machines in the hot pool, warm pool, cold pool. Of course, the underlying Markov chain will be larger or smaller depending on how many machines you put in each of the pools. And and of course, many other high-level formalisms exist, such as like SRN, such as the stochastic activity network, stochastic process algebras, and can generate, store, solve moderate-sized Markov models, and have been extended to non-Markov and fluid or continuous state models. So I've given you a reference here, the very first paper on Markov regenerative stochastic petriness and performance evaluation in 1994, and a series of papers we published on fluid stochastic petriness. This one is from European Journal of Operations Research in 1998. There's a lot more literature available on both these topics. But so coming back to our, so monolithic SRN model is automatically translated into a CTMC or a Markov reward model. However, the model is not scalable as the state space size of this model is extremely large. To show you the example, so suppose that I have 3 machines in each pool, 3, 3, 3. So 3 machines in the hot pool, 3 machines in the warm pool, 3 machines in the cold pool. Then the underlying Markov chain has 10,000 some states, and the number of non-zero edges or arcs in the model are 59,000 something. If I go to 777, I have a 4.8 million states and almost 42 million transitions in my Q matrix. When I go to 888, memory overflow occurred. So I was not able to store the underlying Markov chain. So 888 is a rather small system. 777 is a very small system that I have to solve. So this largeness tolerance approach seems very nice, but it is limited. And for any practical problem, it will very quickly exceed your ability to generate or store Markov chains, let alone solve. It turns out that the time to generate and space to store are the bottlenecks, not the time to solve the Markov chain. So we need to find an alternative method. State space explosion is still a problem. And stochastic Petri nets and related formalisms by themselves are nice, but they are not able to solve the real problems, at least in the context in which I have worked. And so the next approach is what may be called multi-level models or hierarchical models. And this will be called largeness avoidance, because a large Markov model will never be generated, will never be stored, and will never be solved. In this hierarchical approach, in most practical problems, what I have done is used a fault tree or a reliability block diagram at the top level, and at the lower level, I've used Markov chains. And many practical examples of the use of hierarchical models exist, and can also use something called state truncation, which I'm not describing here. And so what we have started originally was non-state space models, which are very efficient and they are very simple. Then we needed to go to dependency capture by means of state space methods, but that led to largeness problem. To avoid largeness, we are advocating the use of hierarchical composition, hierarchical model composition. And these two books, the original Sharp book and the Green book, particularly Green book now, is extensive exploration of these hierarchical models and many examples of real-life systems. So the number of components in systems can be hundreds or thousands. And so my grandson will say the number of states in the Markov model will be a gazillion. I don't know what gazillion stands for, but something very large. And so state space explosion can be avoided, I claim, by decomposing system into subsystems, by modeling each subsystem separately, and then composing submodel results together into the system model as a whole. And the letter H in Sharp stands for hierarchy, hierarchical. So from day one, 1986 was the first version of Sharp released to people. And so from day one, hierarchical models are there in Sharp. And here we are advocating the use of state space methods for those parts of the system that require them, that is heavy dependence, and use simple non-state space methods like RBD and fault tree for those more well-behaved parts of the system. So largeness avoidance, the main reason for hierarchical or multi-level models is to avoid solving large monolithic models. That is for tractability or scalability. In Sharp, it turns out we can mix and match different paradigms to arbitrary levels. Can choose the right paradigm for each subsystem. And note that some tools and approaches use hierarchy merely to specify, and a monolithic model is constructed by the tool anyway. So that is not largeness avoidance, it's largeness tolerance. We are advocating hierarchy not only for specification, but also for solution. And I also want to point out that there are many examples in which hierarchy can be done in which there is no approximation. Hierarchy does not always imply approximation, but many times it does. Most practical problems I've solved have two or more levels, with the top level being reliability block diagram or F tree, and Markov models at the lower levels. So let me now show you some examples. So I already alluded to my interaction with Sun Microsystems, where they were interested in helping me model the availability of carrier-grade high availability software platform. And we developed a model taking into account hardware component failures, software component failures, and various types of recovery. And a hierarchical model was used. And I mean model composition, because models are developed separately and they're composed together. And at the lower level, we use Markov chains and the RBD at the top level. And this work was done in 2000 or so, but published in 2006. So at the top level, there was this reliability block diagram I showed you already. And down below, there were Markov models for each of the subsystems. So, for example, power supply subsystem was modeled by this Markov chain. And various different satellite subsystem was modeled by this Markov chain. So I sat down with the engineers and again repeatedly asking questions. I come up with the models and then it is accepted by them. So notice that there are many different submodels and they are collected together into a top level model. So you can represent this overall hierarchical model by means of what we call import graph. The notion of import graph was first published in my 1992 paper with Gianfranco Ciardo in performance evaluation. Basically, here we represent each submodel by means of a node, and arc represents the fact that the output of this submodel will be used as an input parameter to this submodel and so on. So in this particular case, we have a very simple import graph in this case. Okay, so the next model I want to show you is a problem from IBM. Around 2007, IBM had developed as a high availability system for SIP, Session Initiation Protocol. And they wanted to sell this system to a large telco company, telco giant. And hardware platform in this case was IBM Blade Center. And the software platform in this case was IBM WebSphere. And when they presented this system to the telco giant, potential customer, they said your architecture and ideas are very good, they sound good, but we need some numbers. And so we need measures of system availability and other measures. And IBM was asked to then produce models for these measures. And the IBM engineers that were concerned with this system, they somehow came to me and asked me to help them develop the models to satisfy the customer. So IBM asked me to lead the modeling project, and it turned out that there were two different models to be developed, one to quantify system steady-state availability, and the other to quantify the user-oriented metric called DPM, defects per million. After the work, we published two papers. One paper was published in PRDC 2008 on the availability model, and the second paper was published in ISSRE 2010 for the DPM model. I'm not going to describe the DPM model. It's very interesting in itself and could be a separate tutorial, but I'm going to describe the availability model here. So this is the picture given to me when I started this modeling project. These are two blade centers here, blade center chassis, chassis 1 and chassis 2. And we find that there are 4 blades in each chassis, 1, 2, 3 blades and 4th blade. And each blade had a Linux operating system. This is pre-virtual machine days. So these are single operating system on each single blade. And what they had done is that apart from Linux operating system, there were 2 types of software that the application had. One is called SIP proxy, and the other is called AS, application server, which was really WebSphere application server. Sometimes I will call it WAS for WebSphere application server, and sometimes I will call it AS for application server. And notice that there are 2 web SIP proxies, proxy 1 and proxy. This should be blade 2 and proxy 2. I'm sorry. After this many years, I had not noticed this error, minor error. And app servers there were 6 here and 6 here, 12 app servers. And app server 1 in this chassis and app server 1 in this chassis are coupled together in what is called a replication domain. Okay, so given this picture, hardware configuration is 2 blade center chassis, 4 blades or nodes on each chassis. And they told me that one chassis would have been enough from the perspective of performance. So they're using 2 chassis for redundancy. Software configuration wise, 2 copies of SIP proxy, 1 would have been sufficient for performance. 12 copies of WebSphere application server, 6 would have been sufficient for performance. And each app server instance forms a redundancy pair or replication domain with a corresponding application server installed on another node on a different chassis, as we have shown in the previous picture. So system has both hardware redundancy and software redundancy. Is that clear? System has hardware redundancy because it employs 2 chassis rather than 1 chassis that would have been needed otherwise. And it has software redundancy in the sense of 2 proxy servers instead of 1 proxy server, 12 app servers instead of 6 that would have been required for performance. But now let's pause for a minute. Hardware redundancy, we all know, multiple identical copies, as in this case, 2 blade center chassis. But software redundancy, what do we know about software fault tolerance, software redundancy? In the 70s, when people started to worry about software fault tolerance or software redundancy, they quickly came to the conclusion that the kind of thing that we do in hardware will not suffice in software. Because if 1 copy of software is to fail, then the identical copy will also fail on the same set of inputs because it has the same bugs as the other copy. And therefore, they came up with the notion of what is called design diversity. That is, you to the same specification, you construct multiple software versions which are diverse. And this was called design diversity, So classical techniques of software fault tolerance are called design diversity. And then there are multiple ways of using them. One of them is called recovery block from Newcastle upon Tyne, University of Newcastle upon Tyne in UK. And second is N-version programming from UCLA in the US. So design diversity. So you use multiple diverse versions rather than identical copies. But what we find is that the cost of producing 1 version itself is very high. So cost of producing multiple versions is prohibitive. And therefore, this idea of design diversity is very nice, and literature is full of that on software fault tolerance, but it's expensive and not much used in practice unless we're talking about life-critical systems. So, and yet we require our software not to fail. And so we need affordable software fault tolerance. And what we find in this IBM SIP is what we now end up calling environmental diversity. And so what is this environmental diversity is what I want to quickly explain to you. So software redundancy in SIP application server that I just showed you is identical SIP proxies are used to back each other up. So one SIP proxy fails, the other one will take over its work. Remember, they are identical, so they have the same bugs. Both SIP proxies have the same bugs. Similarly, WebSphere application server 6 were needed, but 12 are used, and one, the buddy in the replication domain backs up the other. So whenever one app server fails, its work is failed over to the other app server. They are identical, they have the same bugs, but they still expect the other app server to work. So type of redundancy that we see in real life system is not design diversity, but replication of identical software copies. This is not what the literature, the academics tell you. And the normal recovery after a software failure uses time redundancy. restart software, reboot mode, or fail over to an identical replica. Only when all else fails, software repair is invoked. So this is very different from what you learn in your textbooks and your courses. So this triggered me to think hard as to why should this work. So retry, restart, reboot have been known to help in dealing with hardware transient faults. But in the context of dealing with failures caused by software bugs, why should it work? And if yes, does it work? And if yes, why? Similarly, failover to an identical software replica that is not a diverse version, does it help? And if yes, why? 30 years ago, this would be considered crazy. But today, this is routinely being used. So here, practitioners are ahead of theoreticians. And so I started to wonder as to why this should work. And my proposal is that there are different types of bugs in software systems. And the only model of bug that we used to have, mentally anyway, is now called Bohr bug. That a fault that is easily isolated and that manifests consistently under a well-defined set of conditions because its activation and error propagation lacks complexity. And if this is the only kind of bug, then it is true that if one copy fails, the identical copy is also going to fail on the same workload. But we find that there are bugs which are more complex, and these are now called Mandel bugs, whose activation depends not just on the workload, but also on the environment in which the software is operating. And this environment refers to other applications concurrently running, interactions with the operating system and hardware and so on. And these bugs are called Mandel bugs. And we have done considerable work on this to actually point out what are the Mandel bugs and what fraction of bugs in real life systems are Mandel bugs and so on. And one kind of Mandel bug has been identified as aging related bug, ARB, things like memory leaks are the ones that contribute to this aging related bug. And this then gives rise to what is called software aging and software rejuvenation. And there is a recent monograph handbook that we completed on software aging and rejuvenation. And very easy reading on this classification of bugs is this paper in IEEE Computer in 2007 that Michael Grotke and I wrote. This is perhaps the only paper, maybe one of the few papers that I've written that has no equations whatsoever. So it's a fairly easy bedtime reading if you like. And there's considerable work on this issue of these three types of bugs. And so my feeling is that this environmental diversity, as opposed to design diversity, is that our claim is that this retry, restart, reboot, failover to identical software copy may well work, since failures due to manual bugs are not negligible. And we does have an affordable software fault tolerance technique that we call environmental diversity. And there is a recent paper that is accepted and which will appear in IEEE Transactional Reliability, where availability analysis of a system deploying sequences of environmental diversity-based recovery methods has been done. And there is a previous paper where I worked with people from Tata Consultancy Services to examine some of the failures that they have observed in practice in their consulting practice. Rajesh Mansharamani and Manoj Nambiar were at TCS at that time. Manoj Nambiar still is there at TCS at this time. So back to our availability model of the SIP on WebSphere, which was on Blade Center. And once again, it may be time to do a short 5-minute break. We'll be back at 12 sharp. Thank you.